yet another version. I don't know if this is really necessary. We did this already. Right? So here's that fopen command. We've already seen this. When you put in fopen, what do you want to make sure you always have? Close. Okay. The same format as before. This is the name that you're going to call it inside the program. Anything you want. This is the name that actually exists for the file in the directory. Okay? And this says, I'm going to write text, not binary. Okay? So, these fprintf, that's the print command. You put in the name of where you're going to print it, what's in the file name, using the internal file name that you make up. And then you can put in any quotes you want, and you can add variables if you want. This isn't putting any variables because this part is only printing the labels at the top. So skip a line, print these words, skip a line. Skip 2 more lines. Print this. Alright, skip a line. Skip another line, print this. Skip a line. Then he comes into here, he makes some calculations. And he's going to calculate 10,000 points. K starting at 0, going by H. Actually, where's H? H to 10,000. You see it? Oh, here it is. Initialized 10. Okay, so I'm sorry. It's not 10,000. It's going to be 1,000. It'll go from 0 to 10,000, but the step size is 10. So it'll do this loop 1,000 times. For 1,000 times in a row, it comes in here and it says, if K is equal to 0, so that's the very first time. After that, that won't be true anymore. Right? So I'll just point out, from an efficiency standpoint, putting this test inside of the loop is probably not very smart. Because it's going to do this loop 1,000 times. It's only going to be true on the first time. So I would say, take this out, put it above the loop. And just do it one time and then start the loop. Okay, but it's inside the loop. It'll work. It just won't be very efficient. So if this is true, it prints this the first time. What is it printing? 2 numbers, K and T0. It uses the 8.0 and 8.4 cycle. Okay? Then it skips a line. Every other time it comes through, it says if K is equal to 2,000, equal to 4,000, that's the OR. Equal to 6,000, that's OR. Equal to 8,000, that's OR. Equal to 10,000, that's an OR. So anytime that's true, any one of those is true, the statement is true, then it prints. So how many times is it going to print? It goes through this loop 1,000 times, and how many values get printed out? 100? Is that a random guess, or is your logic? Why do you say 100? It's going to hit these 2 statements. It's going to do these if this one is false and this one is true. Right? That's the logic. If this is true, it's going to do this statement and go to end. If this is false, it's going to check this statement. If this statement is true, then it will do it. Is it 6 or 5? I think it's only 5. Yeah, I think 5 times. Because 5 times, this will be false and this will be true. Okay. Then at the end, it closes the file. So this is going to calculate 1,000 times and print 5 lines. That's the print from that first if statement that I said it's going to be true only 1 time, but it's in there for the whole 1,000 times. And this is the 5 if statements. 2, 4, 6, 8. Okay. Back up just a second. Inside of the program, I just want to point out again these names, because I think this is a slip feature, but it's also one where you can make mistakes. Inside of the program, the file is called file out. here, when you do the print command, you say fprintf file out. That's where you write it. But where does it end up? It ends up in a file called report.txt. It's a separate file. That's the point. Because you're now writing this outside of that file. Okay? Okay, that was an easy one. F13, chapter 514. You can do user-defined functions in MATLAB just like in C++. The functions are separate in files. Just, if we just pause this for a second, I'll just say one thing about this, that again, I hate to sound like I'm always saying the same thing, but the way that this handles these external functions that you create, your own functions, I think is easier for you, much more logical than C++. So if you were to make up a function in here, you make it up as an in file, you put it in the directory that you're going to call MATLAB from, and you can call that function anytime you want from any other MATLAB program without ever declaring it or defining it again. Okay? As long as it exists as a separate in file, and it's in the directory that you're running when you are in MATLAB, you can just call that name anytime you want in the lesson. Okay? So he's created two separate in files here. One he's calling the main program. That's to show how to call a function. And the function is in a different in file. Alex, you've got a really good time. Every time I try to point something, you move the screen. Move back up for a second. Okay, the function is in this other name called curve.m. Okay, so his editor, right, the editor has multiple files open. Right now what we're looking at is this one, the main program, but there's another file open called curve.m. So now, see how this is highlighted? So this is what curve.m looks like. It's these commands. So in the main program, if you see on the right-hand side somewhere, curve, right, here it is. So new grades equals curve, there's the two arguments. MATLAB goes into the directory and finds that program, no matter whether it was created 5 minutes ago or 5 years ago. It finds it and uses it. Okay, now let's go. Yeah, maybe let's go back and let's talk about by reference and the names, okay? Variable names are local because they're in separate in files. The variable names are local, even those in the arguments. So what does that mean? It means that if I put up here, if I call it grades, curve of grades, and down here in the function curve, the name of the function down here is, well, new grades is going to be valued, curve of GRDS. So up here, the value that is stored in the name grades gets passed to here, the values that are going to be stored in GRDS, a different name. The names are local. Same values. The values of grades up here are passed to GRDS down here. This is just an example of running it. It's not, unless you're going line by line in the program, it wouldn't be obvious. But the intent of what this program called curve is supposed to do, do you use that expression in TNUT for grades? This is used all across the U.S. Curve grades. So that example was to show you how to curve, not to show you how, it was an example of when you might curve grades. What's the idea of curving grades? Well, let's say that you have a scale that says something like this. 90 to 100 should be an A. 90 should be a B, 70 to 80 should be C, right, something like that. So I calculate all the grades for everybody, and I find out that if this is the grade 100, and here's the numbers. There's 1, 2, 3, 4, 5. So maybe I find out, is this what I'm going to do? No, I think I should do it this way. Here's the number, and this is the grade. So 100 out here on the end. So maybe I find out that there are 4 students, and they have an average of 40. And then I find out 6 students have an average of 45. And then maybe 5 students have an average of 50, and so on. Maybe the highest average in the whole class, 2 students have an average of 75. So the range of grades is 40 to 75 for the whole class. Now, according to this scale, a few students would get C's, nobody would get A, nobody would get B, right? So what do? In the U.S., we say you curve the grades. You curve them. So what I want to do when I curve the grades, basically, is shift the x-axis so that the highest grade gets moved up into this range, and then there's some more grades, maybe in this range, definitely some in this range. Right? So the idea of curving is to move. Now, different professors have different philosophies about curving. Some just add the same number to all the grades. So let's say that the average here, if the average here is something like 55, and they think that the average over here, the average of all these scales should be something like 75, they just take 20 points. They say the difference between what I have, 55, and what I think it should be, 75, 20 points. So I just add 20 to everything, and that becomes the new grade. When I curve, that's usually what I do. I just calculate one number. What this program did, though, it's a little bit more complicated calculation, so it's probably a better example of showing a calculation. It's probably not a better example of how to curve grades. But he curved according to the percentage that the grade already had. So he decided on a curve from, his average without the curve was 69.1. He wanted the new average to be 75. Okay, so that difference is 5.9. But he didn't just take 5.9 and add it to every score. He scaled 5.9 according to the percentage that the student already had. So a student that had 75 over 100 gets more than 5.9. A student that had 55 over 100 got less than 5.9. Okay, so his curve factor was not applied evenly across the class, but the average of the curve factor that he applied was 5.9. So when it was all done, the class average was 75. Okay? So you can look at the logic of how it is. Okay, let's go to the next one. Okay, so remember we just said all variable names are local. If you want to pass global variables in MATLAB functions, you use this command called global. If you do this, then the same name is used by the main and the subroutines, and they write in and out the same location. If you don't do this, they don't write in and out the same. Okay? So you just use this global. And he says, to help him remember when he needs to find a global variable, he always uses all capital letter names. So his global variable is called grades, all in capital letters. So it looks like it's shouting at him. That way he's more likely to remember. That's the other thing. Okay. And you need the same global command in the main program and also in the file. So personally, it's not obvious to me that you really need to use global variables for it would help save memory. If you really have huge files, but that's almost never a problem anymore. So I think you don't really need to use global variables very well. Okay. the main point of section 5.13. What was that about? MATLAB functions, exactly. Right? And what are the main things that you remember about MATLAB functions? Yeah. In C++, if you use a function, right at the top, you have to have a declaration statement, and you have to include the language of the function inside the program. You have to copy it in there. MATLAB, you just create an int file, and it only has to sit in the same directory, and you never have to declare it inside the program. If you want to use it, you just call it. You just put curve in there. And you can call it in any other program you want. You don't have to declare it in any of them. You just call it anytime you want to use it. So that's one thing you should remember. Second thing you should remember is that there is a difference between local variables and global variables. So if you are confused about how you want to use them, you should probably go look at help global or help function and read what it says and just remind yourself how you're supposed to use it. But if you use global, then you have to have the global statement in the main program and the same global statement in the int file, so that MATLAB knows that you're talking about the same location. If you use local names, it doesn't matter whether they're the same or not, because MATLAB will use two different locations. Okay? So in the main program, I call the function. If I use a local variable A in the main program, I can give it any name I want in the function, including A. I can even give it the same name in A. So to my eyes, it looks like the same thing. To the computer, it's two different places. There's the main A and the function A. If I say it's global, there's only one place, A. And when you call it A in the main or A in the local, in the function, it goes to that same location. That's global. In not global, local variables, A in the main program and A in the function are two different places. Two different sets of ones and zeros inside the computer. Okay? Alright, so let's see what happens with these functions. If you type data fun, there's a bunch of different sets of functions. So this is sort of like a specialized version of that help command. This is another one that you don't really need to know. You should always try to find it at help. But this is a handy way. If you want to see certain sets of functions, you can type help and then the name of the set, and you'll get a nice list, with a few words. It's not too long, which might be plenty. That might be all you need to see, because that will remind you what it is. If you're still not sure, then you can go help for any one of this. Okay? So those are data functions. And here are the categories of functions. Okay? So this is a really, really useful thing to know exists. Because now if you think you want to know something about polynomials, you can say, show me the polynomial functions. And then you do help polynomials. And it'll show you all the polynomial functions. You can do linear algebra. And it'll show you all the linear algebra functions. Yeah, mathematics, right? Then you can worm your way in even deeper. You can do math, linear algebra. Okay, polynomials. Okay. Anybody have any questions about that? One problem that you will have in MATLAB, that I have in MATLAB, and that everybody has in MATLAB, is a lot of these functions, as I said before, were written by real experts in the field that they belong to. And if you're not an expert in that field, you may have no idea what the function is talking about. So this is polynomial curve fitting. I think we can all know what that means. Who doesn't know what polynomial curve fitting means? So curve fit, we talked about doing this with these squares. I have some data points. I think there's probably some function that should describe them. So I'm going to see if I can come up with a function that fits in pretty well. if that function form is going to be a polynomial, then I can use the polyfit function to find that polynomial. And we talked about the first kind of polynomial, right? The zeroth order. What's a zeroth order polynomial? Some constant value, right? First order. It would be a variable, but if I plot it, what does it look like? A line, a straight line, right? Second order. Yeah, it's a pump. This would look like a parabola. Or maybe a hyperbola. Maybe even a circle, right? Depending on what I choose. So third order and so on. One truth about polynomial curve fitting is each next order in the polynomial has another term. So the constant would look like, say, g. The straight line would look like ax plus b. The second order would look like cx squared plus ax plus b. The third order would look like dx cubed plus cx squared plus ax plus b. If I try to fit b to this curve, I just get one number. If I try to fit ax plus b to this curve, I get two numbers. If I try to fit cx squared plus ax plus b to this curve, I get three numbers. If the curve I'm trying to fit has 5 data points, any polynomial smaller than fourth order can't be guaranteed to fit. Because, say it's second order, I only have 3 points that I get to pick. If I'm trying to match 5, there's no guarantee that I can find 3 points that will match 5. But I can guarantee that I can match 5 points if I use a fourth order polynomial. Because that would have 5 constants. So this polyfit, you can do polynomial curve fitting, you can tell it how big of a polynomial you want, you give it the data, and it will calculate for you the best fit of these coefficients. Okay? So if I tell it I'm going to use a first order polynomial, that says try to fit these 5 data points with a line. Maybe the best line looks something like that. It has a y-intercept, the b value, and it has a slope, the a value. This will calculate a and b for you. I can look at it and say, not good enough. Let's try it again. Fit the best second order polynomial. MATLAB will do it. It will tell me what c and a and b are. Then we can plot that, some kind of parabola, and I can say, yeah, that's much better. But maybe I still think it's not good enough. Go to the third order, go to the fourth order. So this is great because you can just tell it whatever order you want, and it'll tell you what the best fit is in that order. It's doing the least squares calculation for you inside. So that's just an example. Okay, let's go through the. See, that's a misprint of that. That should be polyfit, not polyfit. So here's the vector of the 2 data points, right? That's the x and y coordinates of the points you're trying to fit. Tell it how big of a polynomial you want. You can't ask for n equal to 0. That doesn't have any real meaning. So n equals 1 is the smallest. That would be your straight line. N equals 2 is second order quadratic. And it returns the vector. And the vector are the coefficients of the polynomial. And really the only way you can screw this up is if you got the order wrong. So when that vector comes back, the first one goes with the highest power. So the first one that comes back would be D or C or A. The next one is the next highest power. So if it was third order, the next one would be C, and so on. Okay? Here's an example of a linear fit and a quadratic fit, right? So he's got 2 sets of data. How many points? 1, 2, 3, 4, 5, 6, 7. To guarantee a perfect fit, how big does this polynomial need to be? Has to have at least x to the 6th, right? Has to have at least 6th order. In order to fit 7 data points. Remember over here we saw that if it's, for instance, second order is the biggest term, it has 3 variables in it. So we can fit 3 points exactly. So to fit 7 points exactly, the biggest term would have to be x to the 6th. But he's doing it, he's going to try it with linear, that's this one. And he's going to try it with quadratic, that's this one, the second order. I've never understood that word quadratic, right? Because we talked about hexagram a little while ago, pentagram. The coefficient, or sorry, the prefix quad, this in Latin refers to 4. But for some reason in math, when people say something is quadratic, they mean second order. I've never understood that. I think it's a mistake. I think a couple hundred years ago, somebody used this word wrong, but it became the standard that everybody else uses, and now it's too late. Look at you. Okay. Okay, so he calls polyfit twice, right? And so you come down here, here's the coefficient of the linear fit. That's the output of the first call. The output of the second call is 3. The output of the first one is 2. Because in the first one he said, use a linear fit. The linear fit has 2 unknowns. That's the power on x and the power that's a constant. The quadratic fit has 3 unknowns. That's the thing that goes on x squared, the thing that goes on x, the thing that goes on 4. Then he plots them here. So again, this is another example where he's drawing multiple plots on the same graph with a different number of points. So x and y has 7 points. He's going to make red circles. That's the original data. Right? Then he's going to plot the fit of the straight line. That will be a blue constant line, minus. And then he's going to plot the fit of the second one. That will be green with a constant line. So here it is. And I don't know if you can see the green. Yeah. Okay. The green is actually not a bad fit compared to the blue. It's better. Okay. One more. Show of hands. I want to take a little poll in here. So, how many of you think that this seems like really interesting, including stuff? You don't have to. Don't say yes if you don't believe it. Not very many. How many think this is really a pain in the ass? You wish you didn't have to do this. No. I think. My opinion is it's definitely a little bit tedious to learn because there's so many details. It's so hard to remember from one to the next. Just like learning any language, right? If you remember when you first started learning English. I'm going through this right now in Vietnamese myself. You know, I hear something, it makes sense to me, makes perfect sense. 5 minutes later, I can't remember because it's something brand new. I just don't have good recall. If I use it over and over again, see chow. Okay, finally, I think I got see chow down pat. You know, chow toy, what? Chai bia hanoi. No problem. Da. Bia hanoi da. So I know how to say that. But the other, lots of other things in Vietnamese that I've known how to say every now and then, I also forget all the time. I just need time. I need practice. So I know that you're in that same position with that. Right now, it seems a little overwhelming. You see this stuff. It kind of makes sense when I talk about it the first time. Then maybe go back to the dorm and it's like, what the heck is that? This doesn't make any sense. So I know that could be very frustrating for you. But I hope that you have some excitement about just how powerful this is. This can do so many unbelievable things. You know, your mathematics career up until this point has been based mostly on writing a few equations on the board and solving simple problems, or really simple problems. Like, you probably know how to do a matrix inverse. You probably never did a matrix inverse bigger than 2 by 2 or 3 by 3. Maybe if you had a really bad math teacher who was very cruel, maybe you did 4 by 4 one time, right? MATLAB, in the blink of an eye, will do 1,000 by 1,000. The power of this, the plotting, you know, we just took 7 data points, kind of random data points. Where did they come from? Who cares? We've got the 7 data points. And we want to try to come up with a function fit, two calls to a statement that are only different by one number in the end. One of them had a 1 on the end, the other had a 2 on the end. Did a straight line fit, did a polynomial fit. If you did that by hand, it would take you hours. Then, one more command draws a beautiful plot with 3 different colors. You could have 3 different symbols. You could put a legend on the side, you could put all the labels on there. I think it's just great stuff. So, I hope that the frustration that you might be feeling because this was so fast and you think it's overwhelming right now, I hope that you can forget that some of the time and feel really good about what power it is that you're acquiring. You're getting something in your ability now that's just one of the strongest tools you'll ever use in your life. This is amazing for engineering. And I said it before, every engineer in the world, I think, pretty much now uses this program. It does everything, and it does it better and easier and faster than other programs. Sorry, I hate to say it, but you can see it yourself in C++. If you know how to do this, why would you ever use C++? I don't have an answer for that, because I've been an engineer now for more than 30 years. I never use C++, except to try to help you learn it for reasons that aren't perfectly clear to me, to tell you the truth. MATLAB. Okay. All right. So here's the last couple of functions in MATLAB that we'll talk about. What's that? Yeah, fun. Functions are function components. Okay. So these are written so that another function can call. So 2 common MATLAB functions are F0. Okay, does this sound familiar? Uses the secant method to find function roots. As I said over and over again, that's one of the most important calculations in engineering, is to find the roots of polynomials. And the other one is ODE45, numerically solves differential equations. Okay, so the 2 most important examples are right up here. And this uses a modification of the Euler's method called okay? And maybe you can have Tiffany's 15-30 seconds. Okay. Let's go ahead. MATLAB help is quite good in describing the use of F0 and ODE45. Now, before you go on, back up just a second. Look at all the different AEs there are in here. Remember how I pointed out that you can make up all kinds of different ratios for doing Runge-Kutta? So MATLAB has a whole bunch of them built in. There's something called ODE23, ODE45, 113, 15, I think that's an S, 23S, and so on. Okay? So 4 or 5 is the most common of these. Okay, back up a second. So here's the 3rd order equation, right? You can plot it easily on MATLAB and see this picture if you want it, right? And by the way, I just point out that if you plotted this on MATLAB and you put the grid lines in MATLAB, you put nice grid lines. After you plot it the first time, you can see where it crosses. Then you can go back and create a new data file with the points much closer together. And you could plot from, let's say, -2 to -3. And you'd have a great big picture that only has this little piece in there. And on that picture, you could probably see 3 or 4 significant figures where the line is crossing 0. You just look at the plot. Right? That's something you could easily do in MATLAB. Then you can come back, make a new data file that goes, let's say, from 0 to 1/2, and plot that full size. So it would really expand this picture. And you can see very accurately where it goes to 0. So you could just read them. You could just read the roots off of the plot if you wanted. But that's not fun. Let's calculate it. So okay, so here's the function. And this is the F0 command. Alright, just resting my row for a second. So he's using global to use global coefficients. It's not necessary, as he says. You don't have to do this. But because this is a separate, he's going to put his function in a separate in file, myfun.in. That's why he used the global. So to find the roots of a polynomial, you use f0, and right in here, you give it the coefficients of the polynomial you want, and you also give it an initial guess, which isn't also isn't necessary. Okay. Let's look at the subroutine. So in the subroutine, he says that the function is this polynomial. Whatever coefficient number 1 is, times x cubed. Coefficient number 2 times x2, x squared, sorry, x and a constant. So it's a third order polynomial. So what is the function of this function? The only function of this function is to define the polynomial. Then back in the main program, he says, tell me the roots of this polynomial. So instead of just writing the polynomial right there, he uses a function call, and in the function he tells it what the polynomial is. That logic is not necessary. That's 2 steps that we don't have to use. We can use just 1 step. The point of this, though, is to demonstrate. So you may have an application when you want to call a function like the zero finder of a polynomial, but you need a lot more logic in order to create a polynomial that you're looking to put 0 for. So this might be much bigger and it would make more sense. This example doesn't really make that much sense because it's very easy to just put the polynomial right in there and not use a function call. Okay. So that defines the polynomial, that defines the zeros, and this prints out first the coefficients, and then it prints one root. Because it gave an initial condition, it only goes to 1 root. It goes to 1 in constant. The first one using that initial condition. Does everybody remember how that logic works? You've got a cubic polynomial, third order, so it has this basic shape. And you're looking for these zeros, and you give it an initial guess. Let's say this is your initial guess. And the logic is that the program calculates the slope here, and it knows this height. And if the function were a straight line there, then the correct value of the 0, where it crosses 0, this should be equal to the slope times this height. Right? The slope times the height would give me the change in x value here. So that's the basic idea. So in this call statement, he gave an initial value, x initial. If you start on this initial condition, probably you're going to end up on that group, only 1. Right? And you can't find another one unless you start it over again with a new initial guess that will lead to a different group. So if this was your initial guess, you find that. If this was your initial guess, you find that. And remember, I said to find all 3 of them, what do you need to do? So I have a third order polynomial, something like ax cubed plus bx squared plus cx plus d equals 0. I find the first root. The first root is x equals x, I'll call it 1. x1 is my root. So what I need to do is I need to factor this into something that will look like, I'll call it a prime x squared plus b prime x plus c prime times x minus x1. That would be equal to 0. I need to factor this out, turn it into a second order so I can get the roots of what's left. If I don't factor this out, I'm not sure that I won't just keep getting the same root. It could happen. It could happen, for instance, that this thing looks like this. 3 roots are really close together, and I never give an initial condition guess in this range because it's too narrow. I wouldn't dream of trying one that precise. Right? So one initial guess is out here, one is out here. I try another one here, another one here, another one here, and another one here. I only ever find that root and that root. I never can find that one in the middle because the range is too narrow to get a good initial guess. So How can I be sure that that's not going to happen? The way I can be sure is every time I find a root, I factor it out of the original polynomial, reduce the size of the polynomial by 1. And I won't find this root again because I already removed it from the polynomial. This polynomial does not have that root, so I can't find that one again. I have to find another one. That's how I can be sure I can find them all. Okay, so this is using the numerical integration, ODE45. What you have to do in ODE45 is you have to define the what the derivatives are, you tell it what the derivatives are, and you tell it where to start. And remember, the basic idea is when you have the starting value, you use the derivative to predict the next value, and you give it a step size, and it calculates the next value. And it calculates a new derivative, starting at the second value using the new derivative, it predicts what the third value will be. Starting at the third value using the new derivative, it predicts the fourth value. That's the basic idea. But if you remember with run to cut, it's fancier because actually it jumps back and forth and calculates the derivative at different places in the interval and then takes some kind of an average of it, like 15-30 seconds or 1/6. So, go ahead. So here's where you put in initial condition. Here's where you tell it how long you're going to do the integration for. This is going to go from 0 to 10,000 by steps of 2,000. Then when you call the program, ODE45, the thing you have to put into the program is the calculation of the derivatives. Yes, you have to tell it how to calculate the derivatives. So he's doing it here using a function called y prime. So that will appear as a separate function where it calculates the derivatives. Okay. That does numerical integration. And I can tell you, because I've done it, you can integrate 100 equations at a time, 1,000 at a time. You can create one of those mass spring damper models of a spaceship, of a building being shaken by an earthquake. Any of those things you can solve using ODE45. What changes? What's different from one case to another? Inside of here, where you calculate the right-hand side, this case had only one equation, so there's only one derivative you have to calculate. F prime is equal to this. It's just a single value. In my case, with 1,000 equations being integrated at the same time, I would have to define all 1,000 F primes. Okay? But as long as this function does that, the call statements that do the integration are exactly the same. Because remember, MATLAB always figures out what the sizes you're looking for. You don't have to tell it. So you can set up the logic one time for a first order equation that works. Then you can go back and do 1,000 using the exact same statements. It's great. That's what that was. Okay, so let's discuss a little bit about the course management from now on. How are we going to wrap this thing up? How are we going to like homework, blood projects, and figure out grades? This class will have a final exam. Okay, the final exam will be a written exam, and written exam, and it won't be something that you program. You'll just answer questions. Okay. It'll be writing. Yeah. All of the programming assignments are homework and projects. So you'll get plenty of chances to prove that you know how to write a program. The exam, though, won't be writing a program. The exam will be answering some questions. All right, so we will have an exam. There will be projects. There will be homework. You already have a lot of them. I'm really happy to know you have the CD. Now you have copies of all the exercises. You have copies of all the examples. You have copies of all the homework, copies of all the projects. So, how should we handle this? You've got to feel a little bit overwhelmed right now, I'm sure. Although I I'm happy to maybe have another session today if you want. I'm guessing you probably don't want to. You're probably ready to not have a session for a little while. So tomorrow's not possible. I assume that we won't do it over the weekend. Monday morning at 9 o'clock are the project presentations from, the proposal presentations from the other class. So you also have to be ready for that at 9 o'clock. So let's say Monday afternoon is the next time we meet. By Monday afternoon, how much should you do? I'd say you should try to do everything. All the homework and all the projects, at least try it before Monday. And then when we meet on Monday afternoon,